Hi there, my name is Trishul Chilimbi. I'm a scientist at Amazon. I currently lead an effort called M5 that I'm going to tell you about to bring the power of large-scale deep learning to machine learning systems across Amazon. We do this by training foundational universal semantic representations of important Amazon entities, such as products, queries, shopping sessions, etc. At Amazon, we have access to a lot of rich information about a product that we'd like to make accessible to machine learning systems across the company to help them better address customer problems. For example, we have several images of a product. We also have a lot of text describing the product in the form of product title, bullet point text, product description. We also have a lot of tabular information that captures structured data associated with a product. For example, the sizes a particular shoe is available in, the color options, etc. We also have several customer reviews for product that describe the aspects of the product that appeal to them or disappointed them. In addition, we have search queries that customers use to purchase a specific product. And finally, we know the sellers that offer a specific product. This is a lot of information from different sources and different systems, but we need to use all of this data to build a comprehensive representation of a product that we can vend to machine learning systems across Amazon. The rich product information I previously described is available in multiple modalities: product images, unstructured text that describes the product and includes customer reviews and customer question and answers, tabular data that captures product attributes such as dimensions and their values, and finally, some products even have associated videos that contain useful information. So any product representation that we build must be multimodal. Amazon sells products worldwide in several different countries, and a lot of product information is specialized to the locale in which it is sold to account for cultural differences, among other things. So we want to ensure that our product representations are trained on data from multiple locales. We also need to account for the diversity of languages spoken in these countries and ensure that our representations are multilingual. To better understand a product, we also need to understand relationships between multiple entities. For example, what queries do customers type to purchase a product sold by which sellers? To do this, we need to ensure that we utilize multi-entity relationships to train our representations. Finally, we want to ensure that our product representations are universal because different Amazon teams will use them to solve different customer problems. To do this, we need to use multitask learning with an appropriate variety of diverse Amazon tasks that capture the relevant facets of products that we want to build representations for. These 5 dimensions I described are why we call this effort M5. Our goal is to train and vend foundational universal semantic representations of important Amazon entities, such as products, queries, shopping sessions, etc., to machine learning teams across Amazon so that they can fine-tune these representations for their specific task. So how are we going to go about doing this? Most folks are probably aware of the emergence of powerful language models such as OpenAI's GPT-3, and we employ similar techniques to pre-train a large foundational deep learning model on a mixture of Amazon catalog data, customer reviews, purchase data, and web data. However, there are some key differences. Our model is multimodal, where we use image, text, and tabular data, and are starting to explore videos. And we leverage graph neural networks to learn relations between Amazon entities and use this information to enrich the representation of specific entities such as products. Next, we use multitask learning to continue training this model on a diverse set of Amazon tasks selected to ensure they cover the important facets of a product or entity representation that are relevant to the customer application that'll use that entity representation. We then use knowledge distillation to compress this large teacher model to a much smaller student model that supports online deployment, which means the 99th percentile model inference latency needs to be less than 10 milliseconds. Even for offline use cases, where the latency constraints are not as stringent, this distillation greatly improves model inference efficiency and reduces cost. We then wend these model and representations to machine learning teams across Amazon for them to fine-tune and incorporate into their application-specific models to solve a wide variety of customer problems. Let me say a few words about our approach to multimodal representation learning using images and text as an example. Current approaches to multimodal learning either use late fusion, where the different input modalities are processed separately before being combined at the end, or early fusion, where the different input modalities are combined early on, and subsequent model layers process the fused input. We employ a flexible hybrid fusion model architecture that allows us to explore and select the appropriate point to fuse the different input modalities for joint processing. We also use a combination of losses to align the representations and encourage cross-modality representation learning. In addition to the standard fill-in-the-blanks loss used to learn language models by masking tokens, we use an equivalent approach to mask portions of images. We also use two loss functions, an image-text matching loss and a contrastive loss, for cross-modal representation learning. We've published some of our results on multimodal representation learning at this year's CVPR conference. Another aspect is learning from information about the relationship between entities and using this information to learn enhanced entity representations. For example, consider the graph I've shown that represents customers typing different queries to purchase different products offered by different sellers, where the edge labels represent numeric quantities. We use our models to represent entities, which are nodes in the graph, and use graph neural nets to train the node representations to effectively predict target edges and their labels. A key challenge here is scaling the system, as the graphs and models we use are extremely large. In addition to the work I've described, we are collaborating with partners across Amazon on 5 foundational pillars. Green AI. We focused on efficient training and model inference and are investing in hardware acceleration, compiler optimization, job scheduling, elastic training, distributed training optimization, reducing wall clock time to convergence, sparse model architectures, knowledge distillation, approximation, and quantization. Robust AI. We want the models we train to be robust, which means when we retrain a production model, as we often do, since we currently have 14 M5 powered models in production, we would like individual model predictions to stay the same if possible, and are exploring end-to-end training methodologies to help ensure this. Fair AI. Since these are foundational models, we want to ensure that the data we use to train our models are free from biases. Interpretable AI. Deep learning models are currently black boxes, but we need to invent techniques to explain their outputs. This will help us build trust in their prediction, enable us to use them for applications where interpretability is a must, and also help us to train better models. Privacy-preserving AI. There are benefits to training models that are personalized and understand you better, but we have to ensure that adversarial attacks will not reveal any personal information. Our goal with M5 is to responsibly bring the power of large-scale deep learning to machine learning teams across all of Amazon. Finally, if you're interested in learning more about our open roles, please feel free to check our career page in the description below. Thank you for watching.